I want to spend a few minutes going over the momentum mini assignment that you guys handed in to me on Monday. This is great preparation for our test coming up tomorrow. You've got all your quizzes to go back and study from, review, look at where you had trouble. You've got this assignment to go back and review and look at where you had trouble as well, in addition to other resources as well, of course. First question, number 1 says, 2 carts at the same initial speed move towards each other on a table. Okay, so they're moving the same initial speed. We don't know what that speed is, but we know that if it's 5 meters per second for object 1, it's 5 meters per second for object 2. They're moving towards each other like this. Cart 1 has a total mass of 500 grams. Cart 2 has a total mass of 250 grams. We know that cart 1 is heavier than cart 2, but their velocities, or I should say their speeds, are the same. That means that object number 1 is going to have more momentum than object number 2, right? I don't know if that's going to help me. I don't know if it's going to be relevant to the question, in fact, but I know that that is the case, that object number 1 has more momentum than object number 2. 2 carts collide after contact. They remain separate from each other. They move off independently. So afterwards, they're going to move off this way. Okay, 2 is going to go to the right, and number 1 is going to move to the left. We want to know which of the following vector diagrams drawn to scale shows the magnitude and direction of the impulse experienced by each cart during the contact. Kind of an interesting way of asking a question that we've seen before, okay, and a question that we may very well see again. And that is, how does the impulse on each object in a collision relate to one another? Well, by the law of conservation of momentum, if it's an isolated system, the total momentum has to remain the same. So if one object gains 10 units of momentum, the other object must lose 10 units of momentum. In other words, one's going to be a positive 10, one's going to be a negative 10. That eliminates B and C right now. We can scratch those out right now because those two are showing us 2 impulses that have different magnitudes. That leaves us with with A or D. So which is it, A or D? Is the force on cart 1 going to the left, or is the force on cart 1, the impulse on cart 1, going to the right? Well, here's the way I looked at this. I looked at it and said, look, impulse, delta P, is equal to F times T. So if the force is to the left, the impulse is to the left. If the force is to the right, then the impulse is to the right. Car number 2 pushes on car number 1 this way. Car number 1 pushes on number 2 this way. So if the force on cart 1 is to the left, then the impulse on cart 1 is also to the left. And the impulse on cart 2, same direction as the force on cart 2, to the right. Does that make sense? The other way that you can think of this question beyond conservation of momentum is, funny enough, back to physics 20. Okay, physics 20, we learned about Newton's third law. If object A applies a force on object B, B applies an equal and opposite force on object A. So if forces are equal, well, then the impulses have got to be equal as well because, of course, the time of contact is equal for both of them. So once again, it tells us that we can eliminate B and C, and it either has to be A or D. Get the direction by looking at the directions here. We get the magnitudes by either using conservation of momentum or Newton's third law. During this collision, momentum blank conserved in kinetic energy most likely. Notice that's bolded, so that means not for sure. Most likely, not for sure. Most likely blank conserved. Well, we know that momentum is conserved, right? If it's an isolated system, momentum has to be conserved. At least it's with either C or D. What about kinetic energy? Well, it could be conserved. If it's an elastic collision, they bounce apart, right? So it leaves open the possibility that it's elastic. If they stuck together, we know for sure it's inelastic. If they bounce apart, it could be elastic. It could be inelastic. What is it most likely? Inelastic. Because 90 or 95% of collisions, at least, are going to be inelastic. So you might as well play the odds here, right? You're not guessing. Okay, this is not a question that you're guessing. Understand that. If the question said, kinetic energy blank conserved, well, then you might make an educated guess that it is not conserved. But the words most likely don't involve a guess. The words most likely are telling us use probabilities. The probability is that kinetic energy will be lost. Well, it says they bounce apart as separate objects. But the clay would deform. Okay, so there's another reason to start thinking that it's going to be inelastic. Okay, even if you're dealing with objects that are pretty rigid, and you got to make a most likely kind of estimation, I still want you to pick inelastic because it usually is inelastic any way you look at it. Okay, next question. Again, lots more information about this. It says, a student performs an experiment to investigate the time required to stop a toy van. In each of 4 trials, the student varies the speed and the mass of the van. This, you know what this reminded me of? And, you know, we talk about sometimes, you know, how is this like another problem? Or how is this unlike another problem? You know what this one reminded me of? This reminded me of your first lab, actually. We're varying the speed and mass of the van. What are we really varying? What's really the manipulated variable there? Yeah, the momentum, the initial momentum, right? PI. That's what we're changing there. I don't know if that's going to be important or not, but it's a thought that came to my mind as I'm reading this. The more thoughts that come to my mind, the better, right? All right, the toy was brought to rest by a piston that applies a uniform force that is the same for each trial. I thought this was really important, actually. The force is the same for each trial. Okay, those aren't just context words. Okay, it's important to know that in all 4 cases, the force is the same. Hey, wait a second, though. Didn't we say that the longer the time of contact, the lower the force is? But here we're saying the force is the same in each of the 4 cases? They're 4 different cases, right? It's 4 different scenarios. You got 4 different vans of different mass, and you have 4 different initial velocities. So the impulse is not going to be the same for each of these 4. In fact, we know this one has a momentum of 6, this one has a momentum of 7, this one has a momentum of 9, and this one has a momentum of 5. If the momentum is different, and they all come to a stop, then the impulse will be different as well. That's not the predetermined impulse. If we have different impulses and we have the same force, then the other thing that's going to be affected is what? Usually it's increased time, impulse is the same, the thing that's affected is force. Here it's force is the same, impulse is different. What's the thing that's affected? Time. Let's look at what the question says. When the trials above are listed in order from the trial that has the longest stopping time to the smallest stopping time, the shortest stopping time, the order is what? Well, if we have the same force for all of them, which one's going to take the longest to stop? Right? 9. It's the most impulse. Right? The impulse would be -9, 0 minus 9. The biggest impulse. The force is the same, then time has to be pretty big as well. So if we're looking for them from the longest stopping time to the shortest stopping time, then we're going to look at them from the biggest momentum to the smallest momentum. It would be 3, 2, 1, 4, right? 3, 2, 1, 4. Biggest initial momentum to the smallest final momentum. Particular rocket consists of stage 1 with a pretty big mass, 45,000 kilograms, and stage 2, which has 120,000 kilograms. Initially, the stages move together at 25,000 kilometers per hour. See the kilometers per hour, non-standard unit. I'm going to circle that. So we got one object here moving at 25,000 kilometers. There's a small explosion causes the stages to separate. As soon as I see that word, I think something right away. I think conservation of momentum. As soon as I see the word explosion, or even if it didn't say explosion, even if it just said later, an event causes the stages to separate. Well, it's like an explosion. Okay, even if it's not physically an explosion. If they separate, then we can use the law of conservation of momentum. Now, when they separate, it says stage 1 moves 30,000 kilometers slower, or sorry, 30 kilometers slower, not 30,000, 30 kilometers slower than it did before the separation. Okay, there's definitely something here. I don't know if you caught this, something beyond the units here that I want to draw attention to with my red pen here. It's not a units thing. It's not a direction thing. Remember, the red pen isn't just units and direction. It's anything that could lead to a silly mistake. Yeah. The word slower. What do you think the temptation for people is when they see this question? V1F equals 30, right? Let's make the final velocity of object 130. Is the final velocity of object 130? No, it's 30 below what it was. It's 30 kilometers per hour slower. So that's going to be delta V, not V, right? All right, let's see what we're asked here. Speed of V2 immediately after separation. We said we'd do conservation of momentum, so let's go. PI is equal to PF. Normally in an explosion, we'd like to say the initial momentum is 0. Why isn't it 0 here? Because it's moving. So we're going to say MVI equals M1 V1F plus M2 V2F. M is the combined mass, which is, what is that going to be? 1.65 times 10 to the 5 times V1I. Hey, can I do that? 2.5 times 10 to the 4? Do I have to convert that to meters per second? No, you don't actually here. Okay, this is the only thing in this unit that you don't have to convert. Conservation of momentum. Why not? Why do we have to convert it to impulse but not conservation of momentum? Yep. The units cancel here. They don't cancel in anything else here, but they do in conservation of momentum. So I can leave that if I want. I don't have to. If you want to convert it, go ahead. M1 is 4.5 times 10 to the 4. And it said, I think, stage 1 was moving 30 kilometers slower. So whatever that is, 25,000, 24,970. Okay, that's the new velocity of object number 1. And object number 2, wait a second. Yeah, that's right. 1.2 times 10 to the 5 times VF. So you're going to do the math there. And when you do, I think you end up getting C, 25,011. All right. Hey, there's 2 that you probably could have eliminated and guessed between 2 if you had to. Which 2 could you eliminate in this one? Put them up on the board here. Which 2 could you have eliminated probably right away before doing any calculations? This thing was moved. Go ahead, Nathan. Yes, A and B. How come? Because they're less than 25,000. Good. This thing was moving at 25,000 to the right, and object number 2 is pushed to the right. It's not going to be going slower than 25,000, right? It's going to be going faster. How much faster? I wouldn't have been able to. I wouldn't have been able to make a good guess between C and D. It would have been a 50-50 guess without actually crunching the numbers. Hey, but 50-50 is better than 25%, right? All right, next one. 2 identical stationary metal pucks were made to collide in a frictionless surface. What is that telling us? Frictionless surface. We have an isolated system in which no external forces are acting there. Puck 1's moving at 6. Puck 2 is at rest. That's all important stuff, but it's also labeled for me on the diagram. You do me a favor in the diagram there. After the collision, the pucks moved as shown on the diagram. We have a funny angle of 36 degrees, okay, 4.85 meters per second, which of course, James, we don't like those funny angles, right? We want to kill those funny angles. Get rid of them. 54 degrees. There's a funny angle as well. Why can't I kill the funny angle of 54 degrees? Why can't I do anything with that? Yeah, I don't know how fast that's moving. That's okay. Don't worry about that. If you can't get rid of it because you're missing a hypotenuse, don't sweat that. Okay, we get rid of it when we can, but can't do anything with it. We're not going to lose any sleep over that. Let's take the 36-degree angle off to the side here. We got 4.85, 36 degrees. This is x, this is y. Cosine 36 is equal to adjacent over hypotenuse. X is equal to 3.9237. Okay, thank you. And we're going to find the y component by saying sine 36 degrees is equal to y over 4.85. What's that going to be equal to? 2 point something? 2.851? Good, good, thank you. Again, 54 degrees, we're just going to kind of leave it where it is right now because we don't know anything about it here. Anything else about it. X components, M1, well, let's say PI equals PF. M1, V1I plus M2, what's M2, V2I? Save yourself the bother here. What's its value? 0. For the X component and the Y component, right? Equals M1 V1F plus M2 V2F. I see a little bit of good news here. A little bit of good news. What is it? What's going to save a little bit of work for me here? Mass 1 is 0.2 kilograms. Mass 2 is? So that means the masses can cancel, right? Because they're all the same. Doesn't happen often, but it does. It does happen. 6.00 equals V1F. 4.85? No, look, it's dead. 4.85 is dead to us. We're never going to use that again. Okay, we eliminated that 4.85. We will never touch that number again. So what do we use in place of it, James? Yeah, 3.9237, good. And it's to the right, so it's positive. Plus V2F. Solve for V2F, and it's going to work out to be, what is that? 2.0763. Yeah? What do we do next? What do we always do next? Sorry? The Y component, right? The Y component's even easier. How come? Because before the collision, they're both 0, right? So you're going to solve for using the Y component of V2F, and then you're going to put them together and use the Pythagorean theorem. But we're still not done at that point. Because when we do the Pythagorean theorem, we've got V2F. What do we want? What do we want? We don't want the final speed or the final velocity. Rather, we want the final momentum. So how are we going to get that from V? Yeah, P is equal to M times V. So this involves X component, Y component, Pythagorean theorem, and then a little P equals MV calculation. Anybody see a shortcut for this? Tony, was your hand going up? No? Right? How was you see it?
Well, I was just going to say, like, find the initial momentum. No, never mind.
The initial momentum will be the same as the final momentum, okay, but of the system, right? Guys? Yeah, okay, yeah, he could, but then, yeah, Bryce said we could take out the M2 V2F right here and replace it with P2F since we're looking for a final momentum. I'm not sure that that would be a shortcut because then we wouldn't have been able to cancel out the masses, right? But it's correct. You could do it. Yeah. The X, you mean?
Yeah, sorry.
Yes. Look, our funny angle of 54, we now know something about it. We now know the X component is 2.0763. So we could, if we wanted to, take a shortcut, Find the hypotenuse of that side using the cosine function without doing the y component and the Pythagorean theorem. Does that make sense? Anybody do it that way? Anybody catch that shortcut? That's okay. Did it work when you did it the other way? Sure it did. How many people got the right answer for it? That it works the other way, right? It just is a little bit more work, that's all. If you spot a shortcut, that's great. If you don't spot a shortcut, that's okay. Don't spend 5 minutes looking for a shortcut that's going to save you 2 minutes, right? Okay, the answer for that one worked out to be C. I think. Yeah, it was. Yeah. All right, now we got a whole bunch of information here. Permanent magnets, we know nothing about permanent magnets yet. We will before the end of the year, but right now you don't. So you can assume that they're either going to explain something about permanent magnets and solenoids, or it doesn't really matter what they are. What does this boil down to? Like you read through all this, and you see a whole bunch of confusing wording stuff here. But what does this boil down to? It boils down to here the magnet is at rest, here the magnet is moving at 1.5, and here the magnet is moving at 4. That's what it boils down to. We want to know, and the question that goes with this, the magnitude of the impulse that the car experiences from position 2 to position 3. The magnitude of the impulse between here and here. Just don't make this harder than it has to be. Don't try to research solenoids. You're not going to be able to do that on an exam. Look at it and say, look, I know the mass of this object. I know the final and initial velocity. We know that impulse is not mv, but rather m times delta v. The mass here was 5.44 times 10 to the 3. And the change in velocity is, well, it's not 4 minus 1.5, right? We got to convert that to meters per second. But whatever that works out to be, 4 divided by 3.6, 1.5 divided by 3.6, plug it in there. And we solve for the momentum or the impulse. And when we do that, for number 5, we should get D, 3.78 times 10 to the 3 kilograms meters per second. All that information for that. Okay, it could have just as easily asked this question as, here's a car with this mass, here's its final velocity, here's its initial velocity, what's its impulse? Could have made it a third of a page, not a page and a half. 6. A 75 kilogram hockey player moving at 10 crashes into a second stationary hockey player after the collision. The two skaters move as a unit, so they stick together here, right? They combine. Both positives, right? That's good. I don't know anything about object number 2. In the collision, the impulse received by the second hockey player was what? Listen, if I didn't read that, hey, as I'm reading the first sentence there, first 2 sentences in that paragraph, I'm thinking this is going to be conservation of momentum, right? Hockey player 1 collides with hockey player 2. Oops, changed my mind. Asks me for impulse. I better do impulse then. If I want to find the impulse experienced by the second player, then I can use the mass of the second player times the change in velocity of the second player. We don't know the mass of the second player. We know the final velocity of the second player, but not the initial. So I don't know what delta V is either. That's not helpful. But again, keep asking yourself, what do I know here, though? What do I know? Like, tell me something else I know about this situation. Well, I know that total momentum is conserved. That means that if one guy gains this much momentum, the other guy loses this much momentum. It's like question number 1 again, right? Except it's not a vector picture or diagram. So let's say Let's calculate the impulse experienced by object number 1. When we do that, it should be opposite in direction, but equal in magnitude to the impulse object number 2. M is 75 times 4.5 minus 10. Well, that works out to be, I don't know. Works out to be C, 413 or 4.13 times 10 to the 2. All right, next one. In 1999, a satellite called Mars Polar Orbiter was destroyed in Mars' atmosphere. The accident was attributed to a programming error in the guidance system. Scientists had neglected to convert some force data from the units of pounds, which is an imperial unit, to the units of newtons, which is a metric unit. The conversion they should have used was this. This is a true story, by the way. It cost them, I forget how many billions of dollars for this program, because somebody didn't have a red pen and somebody didn't circle strange units when they saw them. And they forgot to convert pounds to newtons. If you make that mistake once, then you're going to get a question wrong on your diploma exam. If they make that mistake, then they have their Mars Polar Orbiter being destroyed as it's trying to land on Mars. Okay. See how important it is to notice these things? Okay, this many pounds is this many newtons. That's our conversion factor right there. All right, it says the radius of the Earth's orbit around the Sun is 1.5 times 10 to the 11, and the Mars orbit around the Sun is 2.28 times 10 to the 11. All right, the question says, during an acceleration, a force of 6 pounds was applied on the orbiter for 2.5 seconds. What's the maximum change in speed? Well, we look at this and think, oh, it's an impulse question, right? We get a force, we get a time, it's impulse. F times delta t is equal to m times delta v, and we're looking for delta v here. Looking for delta v. The only problem is, hey, I got strange units. But I know how to convert those. Okay, we should remember that, right? Because that was the whole problem. That's why this thing crashed, because somebody forgot to convert units. Let's do that conversion now. A minute ago, we saw that 0.2248 pounds was equal to 1 newton. Here's how I would do that conversion. I like doing it as a ratio. 0.2248 pounds is 1 newton. 6 pounds is x newtons. See what I did there? It's ratio and proportion, right? X ends up being equal to, I think it was like 20 something, wasn't it? 26 or something? 26.7 newtons. So now we got this, we got this, we got this. Solve for delta V now. Right, and we did that. Number 7 worked out to be A. 1.06 times 10 to the minus 1. 8. I think 8 is probably the ugliest question on this paper, maybe. Is the orbiter moved 5,000 meters per second? Okay, this is how fast it was moving before the collision, or before an explosion, before it ejected a short burst of fuel. Had a mass, by the way, from the previous page of 629 kilograms. Okay, that's what's happening. Now, after the collision, it says the fuel went perpendicular. Okay, what does that tell us right now? Perpendicular. Down or up, it's a two-dimensional thing, right? So it's going to be an x and a y component. Conservation of momentum in 2 dimensions. I'm going to say it's going up so I can deal with it as a positive. Let's say if that fuel goes up, we'll call that object number 1, the fuel. It has a momentum of 1.37 times 10 to the 5. Where do you think the orbiter is going to go? Object number 2, the orbiter. If it was moving to the right, but I fire fuel upwards, it's going to keep going to the right, but also go down. It's going to go down this way, right? We want to know what that angle is. We want to know how far it was deflected from its original direction. It was going to the right, now it's going down and to the right. What's the angle in between that? We're going to say total initial momentum of 629 times 5,000. The final momentum is, well, this guy is 0 plus 629. Hey, good news is the orbiter didn't change mass dramatically, so we're going to still say it's 629 times VF, the x component of object 2. Get VF. I'm not going to go through the process of solving for that. You can do the same thing for the y component, but the initial momentum here would be 0. It's equal to 1.37 times 10 to the 5. Don't need to multiply m times v here, because I already got m times v. I already got the momentum given to me. Let's add that to 629 VF, solve for VF. And then you're just going to do your triangle and then your Pythagorean, sorry, not your Pythagorean theorem, but the inverse tan function to get the angle. So this guy is going to be here, here, solve for the angle. And when you do that, I think it worked out to be B 2.49, didn't it? Hey, listen, if I had to have guessed on this, I would have guessed either A or B. How come? Why would I have not guessed C or D?
Because it says in the question it's a short burst of fuel.
Yeah.
And this would be required for a long, because it's such a large mass.
Yeah. Yeah, and in the end, like a short burst of fuel is probably not going to change the direction by 87 degrees, right? Okay. Because then what do you do if you don't want to change direction very much? Well, you can't go much less than a short burst of fuel, right? All right, and we got one more question. Standard baseball has a mass of 145 grams. 145 grams, 160 kilometers per hour, reverses direction, attains an even larger speed in the opposite direction in a very short period of time. Oh, wait, we got another speed here, and even another speed here. Reverse direction. Let's make this positive and this negative. Where's the 160 come into play here? We got 160, we got 130, we got 140. The ball's coming in at 130, reverses direction goes at 140. Where's the 160 come into play? Where am I going to use that? It doesn't, right? Okay, be ready for that. Given they give you a number that doesn't matter, that's irrelevant. Graph below shows the force on the bat acting on the baseball as a function of time. Oh, wait, force versus time. Right away, I should be thinking 3 words. Area equals impulse, right? So in other words, you're going to say the area equals m times delta v. We don't know what the area is, so we're going to have to go backwards. We know what m is. It's 0.145. And we know what delta v is. Wait, it's negative 140. Oh, we got to convert that to meters per second, right? What is that in meters per second? Bryce, you got that? And the initial velocity would be, what's 130? Okay, whatever we get there for the area, the impulse, we're going to set equal to 1/2 base times height. The base is 0.7, and the height is my max force. Good, yep. Oh, look at that. I missed that. I completely missed that just now. Time is in milliseconds. Isn't that dirty? Okay. Again, once again, though, okay, I circled things in red up there as I saw them, but we should, even after we're done reading the question, okay, one of our strategies should be every single time, pick up the red pen, literally or figuratively, and say, is there anything else that I can circle with my red pen? And look. Okay, don't focus on any of the rest of the question. Just look to see if there's anything that's red pen. Okay? And then I would have caught that. I didn't do that step, and I missed it because of that. Thankfully, you didn't. Is that good, guys?